So this is the landscape that I started off this course with, which is Hadoop on premise. So we are starting with Hadoop as our first main component that we want to learn in the big data landscape. So once we get through Hadoop, then we can look at Spark and data science platforms and visualizations and all that stuff. So this is like the foundation of all the things that we've learned till date. So this is the first piece that we would cover. Again, I'll go through a little bit of Hadoop again. So this is the Hadoop framework, and there are 4 components as it's shown in this diagram. The first one that shows up is MapReduce. MapReduce is the computational part of the distributed framework. So what it basically does is, if you're given a piece of data, how do you quickly process that data to provide quick results? If you have a large amount of data, by taking care of all the distributed computers in your network, and making sure that you don't have to deal with all the overhead of managing these computers and everything. So what it basically means is you have a huge cluster of computers in your Hadoop network, in your Hadoop cluster. How do you make sure that you use all the capacity that you have in a way that you can process that data very quickly, and also not have to deal with all the underlying complexities of it? So it abstracts all the complexities and makes it easier for the users to process the data. The second one is HDFS, which is the Hadoop distributed file system. This helps to store a given file in a distributed file system so that it can be processed quickly. So for it to be processed, for a quick processing capability, you also need a distributed file distribution technique, and that is provided by HDFS. So the beauty of Hadoop or Spark or any of them is you move the compute to the data instead of moving data to the compute. So traditionally, the way people do processing is moving the data to the compute, but here the data is big and the compute program is very small. So the technique that's used in Hadoop is moving the compute to the data. So that's enabled by HDFS and MapReduce framework. Yarn is the resource scheduler or the resource negotiator. The traditional Hadoop one had a lot of problems because of the way it's built. It has too many components all stuck together, and it became a big overhead on the name node. So Yarn provides that capability. It distributes the responsibilities on a lot of other machines. That way, things can be done much simpler. So Yarn is part of the Yahoo. I think Yahoo came up with Yarn, and Yarn made things simpler from the earlier version of 1.0. And this is very critical when you want to run your MapReduce program, because this helps in the scheduling and queuing and all that stuff. And resource allocations and quotas and all that stuff is done by Yarn. And common utilities are all the utilities or the Java libraries that you need for running your MapReduce. So you don't write stuff from the ground up. So some of the libraries are already built for you to be reused, so that you can process the data. So that you can write your program much quickly and process the data. So these are the very foundational parts of the Hadoop framework. So the next thing I would go is, sorry, one sec. Again, into the HDFS part, the data is broken. Any given file that you put into an HDFS system is broken up into blocks. A block is typically 1.8 megs. It can be 64 megs. You can configure it. However, usual enterprises take 128 megs. And these files are distributed in the cluster nodes. So there are 2 sets of nodes, as I've explained previously. One is, one second, I just want to get this is Yarn, MapReduce, and I can't, it's not letting me, Yarn, that's Yarn 2. I want to get to, what is it, the data nodes. Anyways, I wanted to show the data nodes and the name node, but that's fine. So the files are there are two parts in a given HDFS storage system. One is the name node and one is the data nodes, and there are also journal nodes. So the name node is like managing the HDFS tree structure. So all the files that you store inside the data nodes, they need to be managed somewhere. So these the mappings for which block goes where and all that mappings and metadata and accessing is inside it's inside the name node. And the data node the data nodes are where the actual data is stored, and they're also used for computation. So there are two parts for the data nodes. One, they store the data. Two, they're used for the computation of the data. So uh, so uh, yeah, so the blocks and the blocks are now stored in the data nodes, and all this block information goes to the name node on a regular basis, so that the name node can manage the replication as well as fixing the corrupted blocks if there were any. So what the name node does is, when a file has to be saved, once it's broken up into the blocks, then it identifies which data nodes are available, and it puts in a process to actually start copying the data to those data nodes. So the first copy is anyway synchronous, and the rest of the replication is asynchronous. So in that asynchronous process, some of the blocks can get corrupted. Based on the block report, it identifies, okay, these blocks have not been replicated. So it again tries to re-replicate those blocks. And it also manages to, and also there'll be hardware failures. So that is also accounted by the name node. And apart from all this, new data nodes get added to the cluster. If new data nodes are getting added to the cluster, it identifies all these new data nodes, because this process of adding the data nodes is an online process. So nothing stops and starts. And the name node identifies these new data nodes. All these data nodes get added when the system is all up. The way data node communicates to the name node is sending the heartbeat saying that, hey, I'm available. And when these heartbeats have been identified, okay, it identifies that, okay, this data node is now available in my cluster. So it keeps that inventory of all the available storage, and it adds this data node to that inventory. So that is about the data nodes. And so this is about the MapReduce. I'll go in detail about the MapReduce in a few minutes. The one I wanted to show was yeah, this one. So this architecture shows the name node and the data nodes here. The name node holds on to the metadata, and when the client says write the data to the name node will identify all the blocks that needs to be written, and the data goes directly to the data nodes through the name node. Like with the name node giving the directions, the data gets transferred to the data nodes. And there is rack awareness in this. That is, you can actually choose to put all the data in the same rack. This reduces the network complexity, and it actually is a faster operation. Or you can actually have replicas in each rack. That way you can provide more robustness to your data, so that you don't lose the data. However, there is network latencies and other complications that's involved. So that's about the data node and the blocks. Okay, so that's about the blocks. Okay. Okay, the next one I wanted to go in detail was about, did we talk about the multi-node cluster? There's no diagram here. This is all the setup of the multi-node cluster. We'll leave it over here. And then let's look at MapReduce. So till now we spoke about how the data gets stored into the data nodes and how the name node manages the name nodes at a very high level. We can go into the details and what commands and all that stuff is needed. But this is also an introduction to MapReduce. It's not a detailed explanation of MapReduce. But what is MapReduce and why do we need MapReduce? So this is a very simple diagram of explaining a MapReduce program. So let's suppose you have a file like this, wherein you have some text, and now you're trying to do a word count. A typical Java way of doing it on a single machine is actually reading all the lines and putting each word in memory and actually counting how many times this word has occurred in the process. So you read the first line, You break it up into words, put them into memory, and count. And if this word appears again in your memory or in your map, then you add up the counter. So let's suppose you can do this with if your file is like 10 megs or 20 megs, definitely you can do it in your computer. Let's suppose you have files which are like terabytes of data. So this is typically the page rank. What happened is when you go and type in Google, you say I want to know about let's suppose Hadoop. So Google goes and identifies the top file in your sorry, the top ranked URL in its algorithms. This is not basically based on word count, but one of the things is also word count, and there are other parameters. They have like 200, 250 parameters to identify a given URL. But the first fundamental thing that they do is they actually crawl all the web pages. When they crawl all the web pages, they get the content of it, and the next thing that they do with after they get the content is to identify all the important words that are in the web page. The way they can actually identify the words in the web page is like breaking up all the text and then identifying which words are important, and actually ranking those words. So this is one of the most famous algorithm which is used in MapReduce, which is the word count. So let's suppose now you have terabytes and terabytes of data files wherein you have to identify what is the most widely used, so that you can rank whenever somebody wants to search for Hadoop, you can rank the exact file or the exact process in this. So in that case, how do you do it is you actually split the entire content into words and identify how many times this word has occurred in this file. So that's the MapReduce word count algorithm that this is showing up. So this is how it typically happens in a MapReduce program. One is map and the other one is a reduce. Map is to convert a text format or anything in a format so that you can start doing computations to it. That's called the mapping phase. And the reducing phase is to actually take all the data that you have mapped, like all the data which is ready to be computed, and actually running your reduced program on top of it to actually get the results that you're looking for. If you're looking for word count, then your reduce program is actually helping you do the word count of it. If you're trying to do a sum of all the words that are there in that in your what is that in your text file, that is, you can actually do it in reducer or in a mapper only. But yeah, imagine you are doing a reduce only. You can also do how many words start with the letter H. So all these different questions or the queries that you want to run, it typically goes into the reducer, and mapper is basically helping you to convert the text that you have in your file in a format so that you can actually process it in your reducer program. So this is how a typical MapReduce happens. So you have an input file here, which has welcome to Hadoop plus, Hadoop is good, Hadoop is bad. So this is one big input file that you got, imagine. So the first step that happens is you have to break up each sentence in this to start processing it. So the input splits that happen, this happens automatically inside Hadoop. You don't have to do it. This is done by the Hadoop common utils. So the line splitter is the common splitter that you used in a text file. So once you put it into the Hadoop framework, this line splits automatically happen and it comes into your mapper program. And in the mapper program, what you're doing is you're breaking up the sentence, welcome to Hadoop, and you're counting how many times you found that word. So welcome, you found it. There's once, it's found in your map. Two, it's once in Hadoop. Let's suppose you have two Hadoops. Welcome to Hadoop, Hadoop. You'll have Hadoop 2 times here. So this is basically mapping the word and the number of times that you found that word in your sentence. So this is what the map is going to do. So once this has been mapped, that is the word and the count has been identified, then the shuffle happens before the reduce. This shuffle happens behind the scenes. You're not actually doing the shuffle. It's taken care of by the Hadoop framework by itself. So what the shuffle does is it brings all the words which have the same key. So if it brings, imagine this is a key value pair. The key is welcome and one is the value. So I found, so what the shuffle phase does is it brings all the keys, same keys under one partition. So right now, these are the 4 partitions that you have. And once you finished all this, all the 4 partitions, it's now putting all the partitions, bringing all the partitions with the same keys together. So here I found Hadoop 3 times, so that comes into this partition. Is this found 2 times, so it comes to this partition. So once the shuffling happens, then the reduce phase kicks in. So the partition is pushed into the reduce phase, wherein in the reduce phase, you're adding up all the number of times this has happened. So let's suppose this has come like 10 times. Then Hadoop, when you do a sum of all the values here, the value is going to be your reduce. And here, if you see once the partitions go into the reduce program, there you're adding up all the word counts, and this is the final output which gets stored into HDFS again. So once you've run your MapReduce after doing a word count, and you've written your mapper and your reducer, this final results are again stored back into HDFS. Now you can take this file which is processed inside HDFS and you can push it into your databases or your analytical systems or your visualization systems or whatever. So this is how a very high level of a MapReduce program works. So I'll go a little bit more detail about MapReduce, and then this is just still an introduction. You're still in an introductory phase. Once we start looking into programs and everything, that's when you will understand how this works. So the input splits is the one which breaks up the input file into smaller chunks so that you can process them. This is about the mapping, which is converting the file so that it can be processed. And that's the reducing phase. So, okay, I'll talk about the job tracker here. So when you actually submit the task to your yarn system, so the client submits the job to the name node. The name node has yarn. So this is how this is now the part of the yarn system that you're talking about, of how the job has been processed. So there's a job tracker. So when you submit a word count process, that is actually a job tracker, and this acts like a master. In this case, in yarn, this is called an application master. So I will show you a little bit more detailed about it. So let me just start with a very simple introduction, and then I'll take you into yarn. So once you submit that job gets scheduled into all these data nodes. Let's suppose you have to run 3 map tasks. So when you actually submit the task, you will actually, based on the number of partitions, it automatically identifies how many maps to run, or you can actually specify how many maps to run to. So let's suppose there is a default map configuration, or you can say I want to run 3 map tasks. When you identify 3 map tasks, it identifies how many partitions are there, like how many blocks are there of your data nodes, and then it schedules the map task into those data nodes. So let's suppose you have one block over here, one block over here, one block over here. So the map task gets scheduled into those computers based on the availability, if there's a slot available for it to be processed. And this map task is managed by the task tracker. So the task tracker sends the information back to the job tracker saying that this task is being processed, or it's been aborted, or it's taking too long. And if you want to do speculative processing, which is very typical, speculative processing means if something is supposed to take 2 minutes and it's taking like 15 minutes, then something went wrong with the computer and you're wasting your time. So in speculative processing, it will kill that job, it will kill that task, and it will restart it on another computer. So if the task tracker, since it's sending the status updates, it's updating the counters. If there are counters, I'll get into counters, accumulators, and all that stuff in the later task. So it passes on the job status. So if you look at how a job runs, it'll tell you it's 20% done, 40% done. Map is in progress. This map is at this stage. So all that level of status or telemetry goes from the task tracker to the job tracker. And then once the map task completes, the task tracker will inform the job tracker that this map task has been is complete, and you can start the next process. Once all the map tasks complete, then only the shuffle happens, and then only the reduce happens. So it's not like one map is finished and you can start the reduce job. It doesn't happen like that. So all the maps have to finish. if there is a reduce at the end, then all those so the shuffle happens and then the reduce happens. So so the maps here are parallel and the reduces are in parallel. So this is a quick a look at the how the job tracker and the task tracker works. Now I'll go into a little bit into the yarn. Like yarn is the fundamental thing which is actually managing the job trackers, task trackers, map tasks, and reduce tasks. So this is a yarn. This is how yarn looks. So the client submits the job to yarn. So the name node has the yarn and the HDFS. So the manager and the yarn scheduler. What yarn has is a queue. It manages a queue. So let's suppose you submit 100 jobs and you don't have capacity. Then what happens? It waits in the queue. Let's suppose you submit a job wherein you don't have a quota. So the entire cluster is not like everybody can process everything on the cluster. There's a priority queue. So people are given quotas. And that quotas are also managed inside Yarn. So if you don't have a quota today, like you exhausted your 10% quota or 20% quota of your Yarn queue for the resource processing, you have to wait so that the higher priority jobs finish. So once you finished your, once you have quota, then Yarn decides, okay, now I need to run this job. So there are two ways of running a job. So there's a client machine, there's Yarn, and there are data nodes. The client machine is the one which is actually submitting the jobs. It's actually in a typical Hortonworks or a Cloudera world, it's called an edge node. Edge node is something that's sitting on the edge. It's not inside the cluster. So once you are in an edge node, from the edge node or your client machine, you're submitting a job to Yarn, then you have two ways of doing the program. One is to run the driver. Driver is the one which tells is a program which tells like how does my MapReduce run. So it's the complete end-to-end process of your MapReduce, which says I want to run this map, then I want to run this reduce, then I want to run this map, then I want to then do this reduce. Those are all the steps that you want to do in your program. That's called the driver program. You have two ways of running that driver program, one inside your client, or you can run that even inside the cluster. Typically, we always run the driver in the cluster, and that driver, if it runs inside the cluster, is run through the application master. So the application master here is the driver that's running if you're running your program in the cluster mode. So once the application master, that's the driver, that starts running, then it starts processing step by step. So in my word count here, I'll go back to the original word count. Where is that? So here in my word, here in my word count program, I'm telling I want to run one map program that is breaking up the input line splits into words and counting the number of words. And the second one is actually a reduce, wherein I'm trying to reduce it. Sorry, I have to explain one more thing, which is called partitioning here. So I'll explain that partitioning and the improvements here in the later programs. That's why I said Hadoop. If you have two Hadoop words, you can get Hadoop 2. You don't get it without using a certain partitioners and whatever in that. So I'll talk about it in the next few sessions. But however, so in this, if you look at this program that I explained, there is a map and there is a reduce. So all this, how this needs to run is actually written in a driver. And the driver writes in the driver, you clearly have this is the map and this is the reducer. So once that driver is written and it runs in the application master, the first thing that you need to process is, let's suppose you want to run a mapper. In that case, then you have to identify all the data nodes that you need to run the mapper on. So now Yarn identifies all the slots that are available, the capacity that's available, where the data nodes have data, and it will spawn the rest of the jobs into those, wherein the map jobs start running. So no, they're not called map jobs, but map tasks. They start running on those machines. So that's what this shows. And the node manager actually communicates back to the resource manager. So you can see the Yarn node manager, right? And these map tasks that run inside these data nodes are run in separate JVMs. So there's not one JVM that's running all your map tasks all together. So every single map task that you run, it actually spawns a JVM and it runs the map task on top of it. This is a lot fast and quick introduction of it. The reason I wanted to explain is so that we can get a head started and then we can actually go into the depths of it. So this is Yarn 101. So I'm running out of time. And this actually shows you, so there's a resource manager and these node managers are actually talking to the resource manager, and every container that's spawned is actually your mapper or your reducer, and the application master here is actually your driver that's running. So if you see application masters, those are your drivers. The containers are where your map tasks are running, and the node managers are communicating back to the resource manager. So all the job trackers, task trackers are inside these node managers and resource managers. So that is a very short introduction to Yarn. So right now I'll stop the video and I'll take some questions. One second, I'm just going to stop the recording.